Okay, the next and final talk in this session is contribution of chemical processes to infrared emissions from nitric oxide in the thermosphere, talk given by Karthik Venkataramani.
Thanks. Hi. So I'm a grad student with Scott at Virginia Tech. And I've been focusing mostly on the modeling of nitric oxide in my master's, and in my PhD I've been working on the cooling aspect of NO in the thermosphere. Again, most of the talk in the day has been about the UV stuff, so getting into the IR must be slightly sticky for me, but I'll give it a shot. So a point that's been brought up by Justin briefly, and I think Scott earlier in the day, was the density of NO is such that it's a minor species, but its behavior and its importance is more of that of a major species. And Dr. Winnick mentioned this briefly a minute ago. It acts as a thermostat in the upper atmosphere, and how it does that is it extracts the kinetic energy from atomic oxygen by collisions, which goes into vibrational energy in the NO molecule, which gets emitted in the optically thin region above 100 kilometers, 120. So it emits at 5.3 microns, it's optically thin, and thermal energy gets radiated away, so it effectively cools the atmosphere. And when you do high resolution studies of this IR emission, you can find out where that NO came from. If it was produced by NWD, if it was produced by N-S, different flavors of atomic nitrogen. So you can do that if you do high resolution studies of the NO-IR spectrum. And I think Dr. Winnick missed like a few slides at the end of his talk. It's a really good indicator of the long-term energy deposition by the sun in the atmosphere. The last slide that he has was the 5.3 emission versus time, and that emission really tracks well what the sun was doing over 15 years. So there's that. And then what I focus on is this part of the IR emission, which we call chemiluminescence. I'll get into that. But just to stay for a minute longer on the importance of NO, this is from a lay paper, I think 2012, which is for the 2003 Halloween storm. We have here BZ, KP, the sun was really active those days. And this is neutral densities measured by the CHAMP satellite. So what happened was the storm hit, the atmosphere expanded, the satellite sees more drag. And then this is the SABRE data, which shows the IR emissions from NO. So it's cooling the atmosphere. And the amount of time it takes to cool is in the order of magnitude of the day for reasons that I might get into. And you see this recovery, which is on the order of a day. You have another storm that hits, and then it cools off. The NO responds immediately. The energy gets radiated away. So the NO acts as a thermostat above 120 kilometers. So apart from the fact that it's important in the ionosphere, destroyer of ozone, lower below, harmful, a useful fact of NO and its behavior is that it cools off the upper atmosphere. So there's that. So terms that I might be using in my talk, this is the dominant way how vibrationally excited NO gets produced in the atmosphere. The way it removes energy is it extracts kinetic energy from the atomic O by collisions. It gets excited to the V equals 1, vibrationally excited first state in the ground electronic state. And then coming down here, it emits that energy as a photon in the 5.3 micrometer region. But the aspect of emission that I'm focusing on is this chemical production. And what you have here is the NWD and N-S reaction producing vibrationally excited NO. And in a minute, I'll show you why it's important. But when I refer to chemiluminescence, I'm talking about these two reactions. This is the thermal collision. And then the way you lose vibrationally excited NO in the thermosphere is it can get quenched again by atomic O. It doesn't emit. The energy goes back into the thermosphere. Or it can emit a photon, and I'll get into this. It can emit a photon, and it cools the atmosphere. So this is an update to the the Cauchy's experiment. This is a theoretical study showing the vibrational yields, and I have diamonds is NWD, stars crosses N quadrant S, and what I'm focusing on is how vibrationally excited the NO is when it's produced by NWD and N quadrant S. And you see for NWD, you have like a peak right there, it's near 10. For N quadrant S, it's about 4. And what that means is you produce NO in the fourth vibrationally excited state, a peak for N quadrant S. For NWD, it's about that. And this slide really, this image shows that when you produce vibrationally excited NO in the thermosphere, it's probably going to radiate instead of being quenched back. So this is lifetime by quenching, this is lifetime by emission, and the amount of time it takes for NO to radiate down is much shorter than the amount of time it takes to get quenched by O, especially since atomic O density just falls off in the thermosphere. So it's probably going to radiate, which is good, especially when you create highly vibrationally excited NO. It's going to emit multiple photons before it returns to ground state. So that's why we think the chemical part of the emission is important. So if we want to model what the vibration level populations are, you just have to take into account the production and loss processes for every level. So we have V equals 0 all the way to V equals 3. The model that we've built goes all the way to V equals 10. So you have 10 vibration levels. You can populate them by these chemical processes, NWD and quadrant S. N2A is something that Justin's working on. But the yields for these two guys isn't well defined. And then you have loss processes from every level, where you can have radiative cascade by emission of a photon, you can have quenching, or you can have chemical losses. So once you have this model in place, you can couple it with a global 3D model such as the TIGCM, both by the folks at NCAR, and you can get a picture of the global chemical emission from NO, which is what we've done. And as Dr. Winnick previously mentioned, if you consider something like the 2.7 emission, right? So the 2.7 emission, which corresponds to like a delta V equals 2, then those levels are probably populated only by chemistry. None of it's happening by thermal collision. So that's a nice check. You can find out what if your calculations of the NO populations, of the vibrational populations, is correct by modeling the 2.7 emission, which is what we did. We compared our results against the Cirrus 1A data, which had a measurement for the 2.7 emission from NO, and we find pretty good agreement with the model that we have. So that's for low latitude, that's for mid latitudes. Both were day conditions. It was pretty excited. The sun was active when these measurements were taken, and we find pretty good agreement with the model. Okay. So this is like model results, and if you look at the chemiluminescence, it's something that's not usually considered when you study the thermal budget of the upper atmosphere. It's something that's usually ignored, but we find that near noon it's about 25%. That's about 0.1. That's due to thermal collisions. That's due to chemiluminescence. That's 0.1. That's about 0.3. So it's about 1 part in 4, about 25%. And we see that most of the emission comes from NWD right there. Right? NWD is way more efficient in producing NO. Oh, the mouse isn't there. The one on the bottom left. So NWD is way more efficient at producing NO. And then you see that most of the emission comes from V greater than 2, which isn't something that often gets attention. So this was a case for a X-class flare that happened in 2012. That should go. So what this figure is showing is chemiluminescence divided by the total emission. So how much NO cooling is produced by chemical processes versus how much gets produced in all. And what you saw there is going to come around day 66 of 2012, was this enhancement when we had a flare. The chemical contribution is about 77% at the peak near the equator. I'm almost done. Last 2 slides. Just moving on real quick. So that was the flare. That was the chemiluminescence right there in red in thermal collision. So the response of thermal collisions isn't that much immediately after the flare. The days after the flare, when the NO density goes up, that's what takes over. So this is the NO density response. You see the NO density goes up, and the days after the flare, what dominates the process of removing energy is collisions, but at the flare itself, a huge amount of energy gets removed by chemical processes. And real quick, it's about 30% before the flare, or this is the day after the flare. It goes down to about 20%, but if you check out when it comes around, the day before the flare, it's about 30%. It's right there. But then the day after the flare, thermal collisions is what dominates the emissions. So that's kind of interesting. In summary, a significant fraction of the NO that gets created in the thermosphere is vibrationally excited. Chemiluminescence about at noon near the equator is about 25%. Using the TIE-GCM, we can model these populations pretty accurately. But a key point is that we need to figure out what the energy transfer processes is, because the NWD reaction isn't that straightforward as compared to the NO plus O thermal, where you have thermal energy getting converted to radiation versus electronic energy that gets converted to radiation. So, thank you.
Any questions for Karthik? I had a quick one. Or you, so, yeah.
Do you have any portion for non-thermal state atoms?
Could you repeat that?
Do you have any population of non-thermal nitrogen ground state atoms reacting with O2 as fast as
No. No, we don't.
Anybody else? I just wanted to ask real quick on your model at the end, where you're showing the response to the solar flare.
Mm-hmm.
That was your model, right?
So that's the that's TIE-GCM and our model put inside TIE-GCM, driven by Eve radiances, Eve solar radiances.
I see. Okay.
Okay, but what was the question?
That was, I just wanted to clarify
Okay.
where the data were.
For the solar radiance, we took like 2-minute data from Eve. It has 2-minute cadence of the solar radiance, so that's what we're using to drive the model.
Okay, good.
Thanks.
Thank you.